Good afternoon. Today we will continue model diagnostics. Today we will continue model adequacy tests. Adequacy tests. Under this, today's topic is tests of assumptions. Okay. Now let us look back what we have completed so far under multiple linear regression. We have taken this data set, then we have fitted the regression equation with sales volume y and your machine breakdown hours x2 and absenteeism x1, and these are the observed values, these are the fitted values and residuals, and this is your x transpose x inverse that matrix, and which we have used to calculate some of the regression statistics. Analysis of variance we have completed. We have also completed the parameter test. Then today's topic is test of assumptions. One of the assumption is linearity. Now, if you look into the results of the given problem, that is the small company doing business in local city where sales volume is function of your absenteeism and breakdown hours plus error. So, this diagram is related to that fitted value, that is y cap vis-a-vis the residuals, and if there is anything that is departure from linearity, then what will happen? The scenario will be like this. Suppose you took y versus x, then your data points is like this, Now, if you fit a linear model, this is y cap beta 0 plus beta 1 x, beta 1 cap plus beta 1 x, this is the regression line. Then what will happen when you plot the error versus, that is the fitted residuals versus predicted value, you will get the line you will not get straight, you will be that nonlinear part will come here, it will come here like this. Okay. This will be the zero value error part. Now, in this particular figure, when you see the residual versus fitted values, I do not find that any departure from linearity. Now, if there is departure from linearity, first of all, you will be, when you fit the residual with fitted values, you will be getting this type of plot. Next, when there are more than one variables, like this case, then if there is any departure, we are interested to know that for which variable this non-linearity is there. So, that is also possible, and that can be done through partial residual plot. Okay. Now, what is partial residual plot? Partial residual plot looks like this. Here, instead of plotting your residuals versus fitted values, we will plot residual plus, suppose the jth variable beta j xj and xj. Okay. So, from the fitted your y cells volume, then y cap, then you are getting the epsilon, that is these are the residuals, and in addition you have to have beta j xj, then this also you have xj somewhere here. So, all those values, now you require this plus beta j cap xj and this versus this. When you plot, you will be getting a plot when there is no departure from linearity, you will be getting a straight line. Example like this, and your data will be hovering around this straight line. If there is departure from normality, linearity, if there is departure from linearity, then what will happen? In this case, the nonlinear portion will come and it will look like this. Then what is the difference between this plot vis-a-vis the residual plot? This is known as residual plot, and here you see the your nonlinear portion is coming under a straight line which is parallel to y cap, and here this value is 0, error value is 0. Now, in this case, these residuals, these are basically hovering around this line, and here the this points, and it is not 0, it is basically epsilon plus beta j cap xj. So, that is the difference. Now, if we want to see what has happened to our that problem given, if I go by E plus x1 beta 1 versus x1, this side it is x1 and then this side is E plus x1 beta beta 1, then you are getting a plot like this. So, from this plot it cannot be said that there is departure from linearity. Okay. In a similar manner, you can see the other one. So, we have taken two independent variables here. When j equal to 1, it is absenteeism. When j equal to 2, this one is our breakdown hours. So, for breakdown hours plot, partial residual plot, if you see here also you see there is no departure from linearity. Okay. Then what will happen if we find figure like this? Suppose if you plot first residual plot, which is epsilon cap vis-a-vis y cap, this is 0 value, and your plot residual plot looks like this. So, it indicates non-linearity. Now, suppose there are two variables x1 and x2 representing the independent variables. So, you are doing like this, beta 1 cap x1 and this side x1, and you found a curve like this. When you plot for the second one x2, then epsilon plus beta 2 cap x2, suppose this one is like this, but residuals like this. Okay. So, first plot is showing you there is nonlinearity. Second plot, if I say this is A, then B and C, second plot showing that this nonlinearity is not due to x1. Third plot is showing this nonlinearity due to x2. Okay. Should I repeat? So, linearity assumption is vital, and when you collect data, that time suppose you have data y, x1 and x2 like this. So, linearity you just developing your scatter plot. If you develop scatter plot, suppose this is y, this one is x1, and then by seeing the scatter plot you will be able to find out whether there is linearity or non-linearity, suppose y versus x2. Okay. So, plot may be something like this. Even though when there is you are not able to see any departure from linearity from the scatter plot, this scatter plot, what you require to do, even though you require to test the residuals. So, residual test is just confirmation that whether there is linearity or not, because residual will give you little better picture. Even if there is small amount of nonlinearity, that will be captured through residuals. Our second assumption is homoskedasticity. By homoskedasticity we mean that equal error variance. Basically our assumption was like this: suppose you are going through x and y plot, let x is only one variable and you are doing regression fitting, your this one is y cap equal to beta 0 cap plus beta 1 cap, let it be x1, this also x1. So, there are many values on x1 and we assume that here across all values of x1 y's variability remain constant, that is equal variance, homoskedasticity. This is the condition called homoskedasticity. Okay. Now, when you are fitting regression line, you are getting this line, then where this variability part is going, this variability part will be accounted by your error term. Okay. So, if you do the residual plot, you will get the picture if there is heteroskedasticity, it will be revealed. If your thing is like this, suppose your error versus residual plot is like this, there is no trend, nothing is there, then this is a homoskedasticity condition. But what will happen if your plot is like this? Suppose this is the case, your plot is like this, or this side is your epsilon cap and sigma cap, or your plot may be like this. Like this. So, if you do little work, more work here, you can find out that this one is resembling like this one is like this. So, a funnel is created here. So, funnel to right and this one is funnel to left. So, if your residual plot resembles this type of picture, it is a heteroskedasticity condition. that means equal error variances are not satisfied. So, the problem we have discussed are the same problem. When you plot the residual versus fitted value, you see this is like this. So, I have created a funnel shape because it is resembling a funnel shape. So, it simply indicates that the small problem what we have discussed Sittican problem, there is heteroskedasticity. Heteroskedasticity is a serious issue and it is related to the dependent variable. It is a problem with the dependent variable. So, when we talk about heteroskedasticity, it is a problem of dependent variable y. So, later on we will see the remedy. Under remedy we have to transform y. Another assumption was uncorrelated errors. So, here the plot is residual versus observation order versus residual. So, 1, 2 like this, suppose 12 observation, and then there should not, that again this should be random. What you mean to say, there should not be any pattern. So, if there is randomness, fine, otherwise there is correlation between the observations, observed data, which is not desirable. If you see the problem what we have discussed, it is difficult for me to say whether there is a particular trend or not. These data points are limited, only 12 data points, but if we see like this side there is something, some non-linear type of things are coming, but we have seen the for this problem the data is linear. So, here I think it is very difficult. So, whenever you find difficulty, I think there are some quantitative tests also which can be done to see the uncorrelated error condition. The test commonly used in is Durbin-Watson test. Durbin-Watson test of for uncorrelated errors. This test, if I say that DW, it is basically that I equal to 2 to n epsilon I cap minus epsilon I minus 1 cap divided by sum total I equal to 1 to n case, and here there will be square and this I square. Okay. So, all of us know the correlation part also. Suppose what is happening here, if there is correlation, suppose this is epsilon I and this one if I write epsilon I minus 1. So, when your I equal to 2, so if I write 2, then it will be 2, this will be 1. If you write like this, then this will be 3, this will be 2. So, ultimately this will be 12, this will be 11. So, that means if there is correlation for now for different values of I, you can think of that I minus 1 we have given here. So, you can go for different lags also, and then R value will be sum total I equal to 2 to n epsilon I cap epsilon I minus 1 cap by sum of I equal to 1 to n epsilon I cap square. Okay. So, this is correlation. Now, this value should be 0. Now, there is relation with dw and this correlation coefficient. So, it is 2 minus r. So, when r equal to 0, dw equal to 2. So, the Darwin-Watson test, this value, if it is 2, it indicates no correlation. Okay. And if r greater than 1, what will happen? If r greater than 1, if I say r greater than 0, let it be r greater than 0, then this will be less than 2. So, that means this less than 2 means positive correlation, and when r less than 0, dw greater than 2, this is negative correlation. So, most of the softwares give this dw values. So, you find out where what value it is coming. If it is 2, fine, perfectly no autocorrelation. If this value is less than or greater than 2, there is certain amount of autocorrelation. Okay. So, the problem what we have taken, that our CT-CAN problem. So, their dw value is 1.69. Okay. So, it is little less than 2. Positive correlations, little positive correlation is there, but there are it is the point estimate only. You may be interested to interval estimate also, and you have to go for that statistics distribution, and accordingly you will be able to find out. So, we have seen the first one is linearity, second one we tested that I think homoskedasticity, third one is uncorrelated error terms, Now we will discuss normality. I think I have discussed normality earlier with respect to ANOVA, and there what I have discussed, the PP plot, probability plot. Definitely this is related to residuals. What we have done there? We have seen that suppose the residuals coming up to that epsilon cap 1 to n, then we found out the ordered one, that is order residual, like this, and then you will already have that I equal to basically this is suppose in the ordered ordered means for ordered residual I equal to 1 to like this n. Then what you have created? You have created 100 into I minus half by n, and then you have plotted the 2. You plotted this 2, that means epsilon that ordered one and your 100 into I minus half divided by n, and you got a straight line. So, it is basically just making you percentage here only, nothing else. Okay.
I minus half by n is our that CDF.
Yeah, that is the CDF in probability level. So, a software this axis will be giving this one, but if you change the axis, there will be straight line will remain this one. So, now you see that for our data, the problem we have discussed, this one showing like this. So, there is departure, it is not normal. Actually, the interesting thing is that when there is heteroskedasticity, there is also usually normality problem. So that's why if you transform for heteroskedasticity to solve the heteroskedasticity problem, then you will find out the normality problem is solved. Many times normality, if you solve, heteroskedasticity problem will go also. So then another plot I will show you here, that is QQ plot, quantile plot. Okay. So the error is normally distributed. Each of the error term that should be normally distributed with mean 0, and your variance component will be AC square, I think I minus H we have discussed in last class. And so with this, in considering that property, that normally distributed with mean 0 and variance, some variance component, then here you are transforming, you can do this type of things also, I minus half by n, and then also you can use this formula, but there is another formulation which is used, I minus 3 by 2, 3 by 8, I minus 3 by 8 divided by n plus 1 by 4, and it is found that this formulation will give you better result instead of I minus half by n. Here you are, for all i's that this you are getting this probability values, then you are calculating the corresponding z value. Okay. So, z value, and then you are plotting this z value, what we are saying here ai values, this ai values with ei values. Okay. So, earlier you have plotted probability versus the residuals.
Sir, here AI is the ordered AI.
This ordered ei, within bracket it is given, ordered ei. So, then you must get a straight line which will pass through the origin. Here things will be like this. Okay. Suppose this side, if I write that epsilon I or ei, we have written in this ei also you can write, and this side is the z value, what we are saying that ai here. So, this point should lie on this or go around it, and if you get this type of plot, then it is normality assumption is satisfied, otherwise not, and in this particular figure we found out that really it is not normal, our y values are non-normal values. So, the errors also showing this non-normality. So, if there is violation to any of the assumptions, how do you go about it? What you will do so that this violation can be avoided and your multiple regression equation can be fit, or multiple regression modeling can be done. Now, if there is heteroskedasticity, then transform y, and Box-Cox method is one method which is used for transforming y. If there is linearity, you can transform y, you can transform x, or you can transform x, y both, so long if there is linearity problem. So, if there is heteroskedasticity problem, you will be transforming only y, and Box-Cox method is also power transformation of y. If there is linearity, you can go for x, y or both. For normality, we will use Box-Cox method. Okay. Now, what type of transformation is applicable under what condition? Okay. Actually, if you see the regression equation, what you are doing in regression equation, this fitted line is nothing but this is the conditional mean values, that mu y given x, this line all values are like this. Okay. So, if for every value of x it is constant, then the first one is coming into consideration. Sigma square is constant. Sigma square, this sigma is related to the variability, this variability of y for a particular value of x. I told you in last class, suppose this one is xi. They are doing something. Okay. So, what I mean to say here, you see that for xi, this is the sigma value, this sigma square you will write. Now, if it is constant, mean across all values of I it is constant, then you are going for no transformation. We are writing our y dash equal to y. But what it may so happen that suppose the sigma value is a function of your expected y. That means what we are saying that when x expected y means here this value is greater than this value. This value is conditional mu yx, mean value of y given x equal to x1 or x2 or something, whatever it is, let it be x1. This one is for xi. Now, this is the regression line. So, it is increasing. When x is increasing, y is increasing. So, what is happening? This mean value is higher than this conditional mean is higher than this, like this. Now, if sigma square is proportional to expected value of y, so then sigma square is also increasing. So, under this condition, you will go for square root transformation. Okay. Then third one is sigma square is proportional to that mean value or two values. It is similar to that when you talk about binomial case, p into 1 minus p type of things. So, and this is similar to this. Okay. Suppose the expected value of a binomial variable is this is the p, and then this one will be the 1 minus p for the other value. So, under such condition your transformation will be sin inverse square root of y. If your this one the variability y variability is proportional to square of the expected value of y, it is said that log y, and if it is in terms of square or cube of expected value of y, then y to the power minus half, that means 1 by root over y, and if it is 4 then 1 by y. So, these are the different types of transformations what is given in Montgomery 2003. Montgomery and then Peck and Vining, one book is there into Introduction to Linear Regression Analysis, only for regression analysis. That is very good book. Okay. Now, if there is linearity problem, see there are several types of linearity problem. For example, y versus x, when you are seeing your things will be like this, like this, like this, depending on the beta values also, regression coefficient values. So, under these different types of nonlinearity present in the y versus x relationship, Montgomery et al. In the same book, they have given this transformation for different. Suppose this one is figure A, figure B, figure C, figure D, figure E, figure F, figure G, figure H. So, first two cases, because from the bivariate scatter plot you will be able to find out what type of picture you are getting, the relationship. Then suppose the relationship is like this, the first one, then what you will do, your transformation for A and B, you see this and this The transformation is y dash equal log y x log x. This is very useful, because you can develop this scatter plot always. Once you know this, now you see the relationship. Then for figure A and B, that linearizable function is y beta 0 x to the power beta 1. Now if you take log x, log of this equation, then log y equal to beta 1 log beta 0 beta 1 x, that sense it is giving log beta 0 plus beta 1 x you will be getting. And if your figure is like this, C and D, this as well as this, either it is increasing curvilinear increasing or it is decreasing. Under this condition, your linearizable function is y beta 0 e to the power beta 1 x, and your transformation only y, that y dash is log y, and then this linear form will be like this. If your data is E and F like this type of function, then you go for y equal to beta 0 plus beta 1 log x. So, that means you are making transforming x into log x, and you will be able to get a linear relationship. For the last part, that means that extremely that coming very low values after this one, after some values of y is very low, and here also initially low, then again constant values here also some constant values. Then what is happening here, your transformation function is y equal to x by beta 0 x minus beta 1 and 1 by y and 1 by x. So, this will be the case. Okay. It may so happen that you may go get some other form, then what you will do. But I think that this list is exhaustive, almost the form is given, almost all the types of relationships are given here.
Basically, sir, first one or two cases you have to see basically what is the process of finding this. If you know the process of finding this, what is the way, then from our scatter plot you will be able to find
Yes.
into that way.
In fact, curve fitting if you do, then the non-linear part automatically will come. There you will see that what type of equation is possible and whether it can be linearized or not. Now, I will show you another important consideration which is known as Box-Cox method. Okay. Box-Cox method transformation, the transformation is like this. There are several versions of this power transformation. Finally, Box-Cox given this transformation, you have to choose a lambda value in such a manner that it will give you the minimum sum square error, and then that lambda will be put here and your transformation will be like this. Depending on the value of lambda, transformation will be like this. So, while to the power lambda is within bracket, this lambda is y to the power lambda minus 1 by lambda, then y dash lambda minus 1, when lambda not equal to 0, and when lambda equal to 0, this will be y dot log y, where y dot is nothing but it is basically geometric mean. Okay. So, y dot is log inverse 1 by n, this sum of the logs. So, y dot is log inverse 1 by n I equal to 1 to n log of yi, this one, and then you are doing that, you are creating, this is the transform variable transformed y, which will be y to the power lambda minus 1 by lambda y dot lambda minus 1 if your lambda not equal to 0 or y dot log of y if lambda equal to 0. So, you may what you will do then, you will choose several values of lambda. For example, let it be minus 2, minus 1, 0, suppose 0.25, 0.5 by 0.75 like this. Let have to go to up to 2. This side also you can do like this. Then you find out what is this y lambda values. For this, for lambda equal to minus 2, I think you find out, or otherwise this side you do y equal lambda 2, find out that y1 minus 2 minus 2, similarly y n minus 2, but here to the power, it is not to the power minus 2, it is to the power minus lambda, and then you are, when you are writing minus 2 here, you are writing, you are changing all the values here, every values will be changed, each one will be changed. Okay. So, then which value you will, then you regress, your regression equation you fit like this, y lambda equal to x beta plus epsilon, and you will be getting ANOVA table for every case. Suppose I will write lambda values like this, suppose minus 2, minus 1.5, minus 1, minus say 0.75, minus 0.5, suppose minus 2.50, like positive up to maybe plus 2. Then your ANOVA table, one component is there SSE, find out SSE value, here SSE value, like this all SSE value will be there. I can say it is SSE lambda 1, SSE lambda 2, like this SSE let lambda k, some values are there, and then you are plotting for every lambda, you are plotting SSE lambda, you may get like this. So, this is the minimum SSE. So, our lambda is this value, let it may be you suppose 1.5, say. Then you consider this 1.5 and transform the each of the y's values with this formulation and go for regression analysis complete.
So, first to find out this, first for various lambda value, we have to find out the y and find
Yes,
out the SSE.
yes, yes.
So, in that way, means every time we have to do it, and
Yes,
when the SSE is minimum, then
that one, that lambda you will consider for that regression equation, that is your regression equation, and this is Box-Cox method, what is given in Montgomery et al. 2003. This is the way Box-Cox transformation is done. And for our case, that example that we have seen that it is non-linear, no, not non-linear, non-normal and heterogeneous, that is heteroskedasticity problem with that. Then I have seen that ultimately what happened when we have gone for different type of different values of lambda, that power transformation, then see that it is basically the we are going, that is at minus 4, this value is coming almost 144 point something, then 146, 148 like this increasing, but in this zone there is that increase is not much. Then I think it is maybe in minus 2 level also it is 146 point something is there, but we have taken only small amount of data. So, if you take large data that may be different, but it is saying that transformation is required. So, for this test of assumptions, I think these are the methods, and if you have any question regarding this, please ask me. Okay. So, next class we will discuss model diagnostics. Okay. So, after 10 minutes we will start.